Hello everyone, welcome back to our latest lecture session. So I believe we have been looking at some math in the previous lecture session. So let's try to take the bigger picture and understand what we have been up to, right? We have been looking at applications of material balances to various reactors, the three reactors being batch, plug flow and CSTR, right? And then we applied the particular mass balance equations on two different kinds of scenarios. So let's summarize them so that you have a picture of what it is that we are up to, right? So I guess I have a reference equation here which I am going to look at later. Yes. So what have we been up to in general? I believe the first example we looked at was an irreversible reaction A goes to 2B, if I am not wrong, right? And then we applied the material balance equation for the batch and what else, plug flow and CSTR. And how did we do that? We identified the compound. So I believe initially we did the mass balance, or the mass balance was on compound A, right? We then wrote down the relevant mass balance equation. For example, what is it for batch reactor? I guess dC by dt is equal to rate of formation of the compound minus rate of loss. So we know the relative rates of formation and loss of these compound here. What is this compound here? A. It's not being formed, so that's 0, and loss, it's being lost. So we wrote down the relevant equations there. So quickly again, how can we relate these particular rates here? Rate of the reaction will be equal to, if I am not using the term loss, I am just going to use the rate of change of A by the stoichiometric coefficient of A, then I need to use the term negative term here, right? If not, if I just use the term rate of loss, then it's just going to be rate of loss of A by stoichiometric coefficient of A, right? And this is what I have. So obviously rate of loss of A is equal to stoichiometric coefficient into rate of the reaction. And what is that in this case? Stoichiometric coefficient of A is 1, right? Into rate of the reaction is the rate constant times the concentration of compound A, right? I think we also use the different nomenclature in this case, maybe CA, and this is what we have. We went ahead and derived the relevant equation for A, and we solved for concentration of A as it changes with time, yes. And then we also wanted to calculate how the concentration of B changes with time, right? And how did we do that, I guess? So for that we applied stoichiometry, yes. And what did we more or less do? We tried to look at variation of this particular equation here, right? Would be equal to rate of formation of B by the stoichiometric coefficient of B, and using the variation here, we end up with a new equation from which we were able to calculate the concentration of compound B, right, as it changed with time. That's what we did. And with plug flow, it's just replacing T with theta, and that's what we did here. And CSTR, we had another equation that we derived, right, and we went ahead and did that. So once we got that done, I believe in each case we also looked at the check. Check is what's the concentration of A when time is at 0 and also time is equal to infinity. So obviously when time is equal to 0, you should get Ca equal to Ca naught, and Ca should be equal to 0 at time equal to infinity, right? As A goes to 2B and at infinity, right, you are going to have all the A being consumed, and that's what I believe we saw with most of the equations here, yes. And then we moved ahead, right, and what did we end up doing, I guess? We end up looking at an irreversible reaction, yes. We ended up looking at reversible reaction. I am going to summarize that here. I started looking at, I guess, so we looked at a reversible reaction here. A goes to B and B again can transform to A, right. So in this case though, you are going to have whenever you write dC by dt equal to rate of formation minus rate of loss, right, you are going to have both the terms, formation and loss, right. So thus we had issues with solving this, and thus I believe once we applied stoichiometry, got the relevant equation, I believe, right, and then we used the integrating factor, right? And when can we use integrating factor? Let me refresh my memory. Dy by dx plus y into function of x is equal to function of another function of x. So when it's of this form, you can use the integrating factor, and then we had the relevant solution for that, and we went ahead and solved it, right? And I believe this is the equation that we end up getting. So obviously we transformed it with respect to k equilibrium, right? So this is the equation that we end up getting. So anyway, math involved, but that's for your understanding, I guess. You obviously never need to mug such stuff up, right? You only need to understand the basics there, right? So this is the equation that we have. And again, for this case too, what did we look at? We looked at the case when time equal to 0, when time is equal to, I believe, infinity, right? And we also looked at, I believe, what would be the case when rate constant of the forward reaction is far greater than the rate constant of the backward reaction, right? We looked at that aspect too. And what did that give us? I guess it gave us the answer which will be relatively similar, I guess, to A goes to 2B or the irreversible reaction. So this is what we did in the last class, and obviously now we are going to continue with this particular session here. So we are still looking at example of A reversible reaction, A going to B and B going to A again. So we were done with our analysis with respect to our application with respect to the batch reactor, right? So obviously, as you know, for plug flow reactor at steady state, what is the only aspect that changes? So if you look at the fundamental equation there that we derived, for the batch reactor it's rate of formation minus rate of loss dc by dt, and here it's dc by d theta is equal to rate of formation minus rate of loss. So obviously you will just need to replace time with hydraulic retention time in the case of the plug flow reactor, right? So we obviously are not going to go into that in detail here. So moving on, we have the next case, and what is that? I guess that's the CSTR, right? So let's look at how to apply this particular case or CSTR case to your reversible reaction now. So I'm in general not good with mugging up formulas. So let's see again for the purpose of refreshing our memories too. How do we get the mass balance for your particular CSTR? Again, what's a CSTR? A continuously stirred tank reactor. You have flow coming in, you have flow going out, right? And you have concentration coming in and concentration going out. And what is the key here though? That the concentration going out is going to be the same as the concentration inside the reactor, right? And why is that? Because it's continuously mixed, right? So as the system is continuously mixed, whatever is in the concentration of the compound inside the reactor is going to be the same as the concentration that's leaving the reactor, right? So I believe what's the mass balance equation, I guess, right? Let's look at that. V dc by dt is equal to Qn Cn minus Q out C out plus volume into rate of formation minus rate of loss. So at steady state, and also assuming that Q in equal to Q out, otherwise the volume is going to change, right? And what this is going to be? So 0, or I'm going to divide by volume 2, right? 0 equal to, and Q by V into C in minus C out plus rate of formation minus rate of loss. And what is V by Q? That's theta, or the hydraulic retention time, right? It gives you an idea about what does HRT give you an idea about. It gives you an idea about the average time, let's say, a water molecule spends in your reactor, right? Average time the water molecule spends in your reactor, that's given by HRT, hydraulic retention time. So V by Q, theta here, right? So where are we here again? So I'm going to bring this particular term out to the left hand side. So I'm going to have C out minus Cn, and I guess by theta is equal to rate of formation of the compound minus the rate of loss of the compound. So I guess we are done with that, and we are going to use that particular equation here. C out minus Cn by theta is equal to rate of formation minus rate of loss, right. So, here we are going to apply the mass balance on what is it now, your compound number A, compound A, pardon me, and first obviously we need to define the rate of loss and rate of formation. So, what is the rate of loss of your particular compound and rate of formation of your compound? We again need to look at this particular reaction here, right. So, rate of loss of the compound will be equal to the rate constant of the forward reaction times the concentration of A, right, rate of loss of the compound, and rate of formation of the compound is going to be the rate constant of the backward reaction times the concentration of B, right, because how is A being lost? When A goes to B, and how is A being formed? When B goes to A. So, these are the relevant reactions here. So, let us plug them in here please. So, C out minus C in by theta is equal to rate of formation of this particular compound. Where is that please? It is here, rate constant Kb into concentration of B. Let us say I am going to use these terms now, right, minus where is the rate of loss here, and that is here, K forward into concentration of A. And one minor aspect we obviously need to look at is that this concentration of A is going to be equal to this variable C out, right, because as we just discussed, whatever is inside the reactor will be the same as the one going out of the reactor, right. So, I am going to modify that. So, C or concentration of A minus C naught or Cn by theta equal to KBCB minus KF into Ca. So, this is where we are, and what have we been doing up to? I guess we can't solve this equation because we have two independent variables here, Cb and Ca, right, and Cn is a known value, the initial concentration is a known value. So, what do? We look at stoichiometry, right, and what is that? I guess Ca minus Ca naught or Cn by stoichiometric coefficient 1 will be equal to Cb minus Cb naught, right, by the stoichiometric coefficient, which is again 1. So, this is what we have, and so let us try to write this down on a fresh sheet of the board and then take this through. So, Ca minus Ca naught by theta is equal to KBCB KBCB minus Kf concentration of A. And what is the stoichiometry? Minus of Ca minus Ca naught is equal to obviously going to be equal to Cb minus Cb naught, right. So, let us try to transform this and solve for our particular equation. So, what I need to calculate? I need to calculate Cb. So, Cb is going to be minus Ca plus Ca naught, right, plus Cb naught. Let us see if I made any petty mistakes please. Cb, I just took the Cb naught term to the left hand side and open up the brackets, minus Ca and plus Ca naught, looks like I am on the right track, right. So, again we substitute that here, Ca minus Ca naught by theta is equal to the rate constant of the backward reaction times this particular term, and what is that? Ca naught plus Cb naught minus Ca, right, minus the rate constant of the forward reaction times the concentration of A in the reactor, right. And let us try to solve for this, I guess, right. Ca minus Ca naught is equal to Kb into theta into Ca naught plus Cb naught minus Ca minus Kf theta Ca, right. So, if I am trying to bring all the terms with respect to Ca to the left hand side and the other terms to the right hand side. So, Ca is going to be here, and where are the other Ca terms? Plus Kb theta Ca and again plus Kf theta Ca is going to be equal to Ca naught, right, plus KB theta into CA naught plus CB naught, right. And then obviously solving for CA, what is that going to end up with? I guess CA is going to be equal to CA naught plus KB theta times CA naught plus CB naught by, and what else do we have here, 1 plus theta into KB plus KF. So let us just review what we have been up to. So this equation is from stoichiometry, right. Change in A and change in B, we are relating that here, and I believe we substitute that in our basic mass balance equation, right, and that is what we see here, CB equal to CB naught, CA naught and minus CA, that is what we just did here, and we still have the other terms, and transforming that and taking theta to the right hand side, CA minus CA naught equal to KB into theta, CA naught plus CB naught minus CA minus KF theta into CA. Again what do we say, transforming the equation such that we have all the terms with respect to CA on the left hand side, we have CA plus KB theta into CA, right, again plus KF theta into CA is equal to CA naught, taking this term to the right hand side, plus KB theta into CA naught plus CB naught, and here I guess we have CA equal to CA naught plus KB theta CA naught plus CB naught by 1 plus theta into KB plus KF, right. So we have this. So now we need to do our checks again, and what are our usual checks? We check when time is at 0, what is our situation. So how does this equation transform into when time equals 0? CA equal to CA naught plus, not time, pardon me, here it is the hydraulic retention time, right, when theta equal to 0, CA naught plus, as theta is 0 plus 0 by 1 plus 0. So that is equal to CA naught. So that is a check and we are done with that, right. And what is the case when theta is equal to infinity? So let us see what happens there. So CA is equal to CA naught plus, okay, now we have a unique situation here, we have infinity by infinity, right. So how do we go about solving this? I guess here whenever you have this particular situation, when you are trying to look at the limit of a particular what do we say equation, and you have it in the form of either 0 by 0 or infinity by infinity. So we are going to consider the Orbitals rule, right, and we consider the Orbitals rule obviously when we are trying to look at the limit of particular variable, and we are ending up with 0 by 0 or infinity by infinity. So I believe we discussed that we need to look at the derivative of the numerator and denominator with respect to the relevant variable. So here I am going to write down derivative of numerator, and that is equal to what now? What is the numerator here, please? CA naught plus KB theta into CA naught. So this is the numerator here. So derivative with respect to theta will leave us with respect to theta will leave us with KB into CA naught plus CB naught, right, and derivative, and what is the limit, I guess, what is the limit of the numerator once we have taken the derivative, and that is going to be the same case here, right, as we apply theta equal to infinity, that is the same case here. And what is the limit, not limit, pardon me, derivative of the denominator with respect to theta, that is going to be KB plus KF, right, and that again is the limit at infinity to at theta equal to infinity, right. So let us see what do we have here now. I am going to continue this here for the sake of our understanding. So what do we have here? We have the limit at theta equal to infinity for CA is going to be equal to KB into CA naught plus CB naught, right, by Kb plus Kf. So, this is our particular concentration of A at obviously at equilibrium, I guess, right, or at theta is equal to infinity. So, let us try to work out one other particular set and then move on. So, I need to rewrite this particular equation in the next board, I guess, right. So, it is equal to Ca is equal to Ca naught plus Kb times theta, is it, into Ca naught plus Cb naught by 1 plus theta into Kb plus Kf, I believe, right. And so, the next aspect that we are going to look at obviously is that when it is a irreversible reaction, let us say we are now considering A goes to B and so on, and B goes to A again. So, if it were an irreversible reaction, what does that mean? That the K forward reaction is going to be far greater than the K backward reaction, right. So, let us see what we are going to have in that case, I guess. So, it is going to be Ca is equal to Ca naught plus let us say, maybe can I call this 0? Yeah, I will call this 0, 1 plus theta into Kb plus Kf will just be Kf, right. So, that is going to be equal to Ca naught by 1 plus theta into Kf, right. So, if we look at what our case was for our irreversible reaction, A goes to 2B, it should be relatively similar to what we just derived, right. So, we now looked at the specific case when K forward is far greater than K backward, yes, and with that we went ahead with our particular case and try to look at the situation, and we end up with a set of variables that is more or less same as with respect to our example when we looked at the irreversible case of A goes to 2B, right. So, now we will move on to the last aspect, right, in kinetics, and the next aspect, I guess, or the major aspect we are going to discuss after this session is going to be acid and base. But before we move on to the acid and base relevant chemical process, we are going to have to wrap up the aspects with respect to determining, let us say, rate equations, as in the practical relevance is that let us say you conducted some experiment, and with respect to time, let us say you have the data with respect to or of concentration, let us say, right. And let us say you do not have the relevant knowledge about what is the form of this equation, as in what is the mathematical what do we say equation that would best represent this particular data now, right, or you do not know which particular order it is that the of the reaction, I guess, right. So, how do you go about those aspects, let us say, or how do you use the data to be able to come up with your form of your particular equation now, right. And also once you come up with the form of your equation, let us say, you also rarely will have the relevant rate constants, let us say, right, or how would you go about calculating the relevant rate constant or your observed rate constant, let us say, from the given data now, right. So, this is what we are going to discuss from a particular example, but we are going to obviously have a brief overview of what it is we are going to be up to, right. So, here we are going to talk about determination of rate equations, In this context, we have two aspects, right. One would be, let us say, determining the form of the equation or the reaction, let us say, right, and the second one would be determining the rate coefficients, let us say. Right. So, let us say we are going to obviously look at the example in relation to what we are up to here, but again keep in mind that we are looking at a particular case when let us say we have concentration versus time data for a particular experiment, let us say either something that you observed out there in the nature or something that you conducted in the lab, right, and then you are trying to, let us say, you do not have the enough what do we say background, let us say, or there is nothing available in the available literature, let us say, that suggests what the order of this particular reaction is going to be, let us say, right. So, then how are you going to be able to come up with your particular what do we say order now, right. So, you are going to try to fit various models, right, to your particular data, and then look at which model would be the best fit, and from that obviously you will be able to look at your particular form of the reaction or the equation, right. And then obviously let us say the example I guess I have is something relevant to r equal to kc to the power of n now, let us say, right. And now what I am talking about is, let us say I do not know what the order of this particular reaction is, let us say. So, how do I do that? So, I have concentration versus time data, right, and I am going to, let us say, modify this into such a way that I have concentration, or now I need rate versus time data. I am going to come up with a way to be able to, what we say, calculate rate. And how do I calculate rate, let us say, right? It depends obviously upon what reactor or the system it is, I guess, right. So, if it is a batch reactor and it is only first order loss, so the rate would then, as we are going to look at it, is going to be similar to or equal to minus dc by dt. If it is, let us say, what is this now, a CSTR or a completely mixed flow reactor, it is going to be dc by d theta, right, not dc by d theta, but that is for a plug flow reactor, I guess, right. And then obviously for the again the CSTR, you have the relevant equation, but obviously it is not a differential equation, I guess, right. So, depending upon the type of reactor, you can come up with the relevant rate, and then from modify the relevant data, so that you can now have, instead of concentration versus time, you will now be able to calculate rate and the relevant time, right. And then you can fit this particular data, let us say, or in this case looks like in this equation obviously it is rate versus concentration. I can fit this particular data as in rate and what do we say, concentration, or I can fit the model, pardon me, to the data, right, and there get the form of the equation by looking at, let us say, which particular, what do we say, values would give me the best fit, right. So, that is one aspect. And let us say once I do that, let us say, and I can now, what do we say, know the order of the reaction, let us say, right, then I can round this off to the relevant order, right, and then be able to more accurately predict the value of my k here, right. So, again there are two approaches, you can either do rate versus time, right, or rate versus concentration approach, or I can do the concentration versus time approach, right. So, again these aspects, I guess, obviously would hopefully be clearer when we look at the relevant example. So, let us look at the example that we have. So, looks like we have some data, right, in a batch reactor. The key that is that, from a batch reactor in which the contaminant is being removed, let us say, the key is that it is being removed now, right. So, before we go further, let us apply the mass balance, right. So, we know the generic form of the mass balance, let us apply that here, right. So, what do we know? We know that V dc by dt, right, is equal to Qn Cn minus Q out C out plus volume into rate of formation minus rate of loss, right. But here obviously it is a batch reactor, right, batch reactor. So, obviously Qn Cn and Q out C out would be 0, there is no flow coming in or going out, right. And now I am just left with dc by dt is equal to rate of formation minus rate of loss. And here the key is again that the contaminant is only being removed. So, now what do I end up with? That dc by dt is equal to minus rate of loss, right, or that rate of loss is equal to minus dc by dt, right. So, this is the key that we understand, or or we need to be able to garner, I guess, right, from the particular scenario here, right. Again it obviously depends upon the kind of reactor and the scenario in each case, right. And so, the first aspect which we are going to look at is, let us say, if we are trying to fit the model to an equation similar to this rate equation, let us say, right, and I want to now be able to calculate the fractional order of the reaction, as in what is this n now. I do not know what this is, I just have the data for concentration and time. So, this is the data that we have, time in hours and concentration in milligram per liter, let us say, right. So, but I need to be able to calculate the order of that particular reaction, let us say, right. So, now how do I go about that now, right. So, there are different ways. So, if you had sufficient background, or let us say if you were able to find relevant literature, let us say, you can obviously find the order of the reaction from that particular literature, right, available literature. But if not, what can you do? You are going to, let us say, conduct regression, right. So, here obviously we have a new term, we are going to look at what that is. You are going to conduct regression, or what does this mean now? That you are going to fit, what do we say, or look for the model that best fits this data of time versus concentration, and from that you will be able to calculate the value of n, I guess. So, how would I fit my model to this particular r equal to kc to the power of n now, right. So, there are different ways, rudimentary ways, as in if you are looking at approximation, I can look at any two data sets, let us say, and then manipulate it or substitute and get some value of k and some value of n, right. But obviously the issue with such an approach is that, right, you are not considering all the data now, as in your experimental values or your experimentally determined values will have either analytical errors or errors due to the what do we say, due to the analyst itself, I guess, right, due to the working of the analyst, let us say. there are many errors that can creep in here, right. So to take that into account, what's the best approach? Obviously you would like to look at an approach that would consider all the data set, right. So in that case we are going to look at regression, I guess, right. And how do we go about that, right? The approach is obviously to look at the model that would best fit the data now, right. So as in I have, what do we say, y as a function of x, right. This is my actual value or true value now. So let us say I come up with my modeled value, or let us say yi, let us say, right. What would be the model that would be able to predict, right, values that would be similar, let us say, or would be the best fit, I guess, right, for your particular experimental values. That is the key here. So the approach here is more or less that you will minimize the sum of squares, right. And what is the sum of squared error? It is the sum of squared error, I guess. Sum of squared error is equal to obviously nothing but the model value, or the error, I guess, right, between the modeled and the actual value raised to the power of 2, right. Again you are calculating the error, right, and those values which will minimize this error, let us say, would be the would conform to the best fit model, right. So that is the key. But obviously we could have just looked at the magnitude, and why are we taking the square here? One aspect is that the error can be positive or negative. So to be able to rule that out, let us say, to take that into account, we are squaring it, but that can also be done by just looking at the magnitude, right. But we look at the square so that, I guess, or we consider the square, let us say, because you want to look at the, or give enough weightage to the outliers too, right. Anyway, so let us look at the example now. What do we have here? I have to calculate the fractional order of the reaction using R equal to Kc by Rn, or Kc to the power of n. I know that RL equal to dC by dt now, right. So because my equation is R versus C, right, I need to be able to garner or gather data, right, as in here I have only time and concentration, but my model is R equal to Kc to the power of n. So now I need to come up with the rate, let us say, at each of these particular sampling time, I guess, right. So how do I able to calculate that? As we just looked at it in the previous slide, it is going to be equal to minus dC by dt, right. So let us switch over to Excel and get this done, right. Okay, so here I guess I set some stuff up. So now I am going to have to calculate the rate. So it is going to be equal to this particular cell. So here I guess they have different data points, right, and obviously I need to look at what we said difference, it is dC by dt. So here I am going to look at the numerical difference, obviously, right. So it is going to be equal to bracket, and so I am going to look at the difference, obviously, I guess, right. So it is going to be the forward differential here, this minus this, and bracket close, divided by, again bracket start, right, minus this and bracket close, right. So what do we have here? We just calculated the difference dC by dt, I guess, right. So this particular C2 minus C1, right, by T2 minus T1, that is what I have here. So enter, and but I should not get this done, what do we say, just use the same forward differential method for all the other, what do we say, data points, because in general forward or backward differential, which we are going to look at, let us say, will lead to compounding of the errors, I guess, right. Here we are going to have to calculate dC by dt, and we are going to obviously look at the numerical difference here, delta C by delta T, I guess, right. So but the key here is that obviously because of lack of data, we are going for at the extreme cases, right, at time equal to 0 and time equal to 15, for the backward and forward and backward differential respectively. But in general, if you look at the Taylor's polynomial and look at the relevant error, I guess, right, you will see that the central differential is relatively better, right. So let us look at the central differential for this, I guess, is equal to, so bracket minus bracket close divided by bracket close and enter. So what have we done here? We have looked at the central difference as in, for with respect to time equal to 1, I looked at concentration at time equal to 2 minus, let us say, the one at time equal to 0 by T2 minus T0, I guess, right. So enter. So I am going to try to copy the cells, the same, what do we say here, right. So that is what we have here, and enter please. And but for the last cell, obviously, you know, here we do not have enough data to be able to look at the what do we say, this central differential, right, or center differential. So I am going to have to delete these cells and delete, and so it is going to be equal to, so instead of central differential I am obviously going to look at the backward differential here, right. So that is going to be equal to bracket start this minus this divided by minus enter. Okay. So now for these two data sets, right, data points anyway, I looked at forward and backward differential, and for all these data sets, right, I looked at central differential, right. So again here the dc by dt is negative, so obviously as we calculated earlier, rate equal to minus dc by dt, so that is going to be equal to minus 1 into enter. So the rate, I guess, right, and I have the same here. And now let us say what is it I need to do here now. I have the rate, yes, I need to be able to calculate a model value of my rate, right. So again, what is the approach here? I am going to let us say it is a trial and error, you can understand that, I guess. So I need to supply some initial value for the constants of what is this now, k and n, right. So I am going to supply some initial value of for the k and n, right, for the rate constant and the order, right, and then be able to calculate my rate model rate. So for n, let us say I will start with 2, enter, and for k let us say I will start with 0.5, right, and obviously they should be hopefully at least within the range of the expected values anyway, otherwise solver is going to have what we say difficulty in getting that, right. So that is equal to now, so what is my rate model here, right. So let me go back to our particular slide here, right, and let us see where we are here. Rate is equal to kc to the power of n, right. So it is going to be equal to this cell into, and the concentration is here c to the power of n is out here, right, and enter, and obviously I can drag drop this, right, but obviously if I do so, right, you know, I am going to get an error because when I do so it is going to use the successive cells. So I need to keep the relevant cells or k and n values or cells constant. So k here is k2, so dollar symbol and again dollar symbol, and for also the n value or n cell corresponding to n, so dollar symbol, and again 1 second please, and dollar symbol, enter. And so now let us see what we end up with, okay. And now you see that this cell does not change, but the one corresponding to C changes, right. So I am just keeping the cells relevant to this rate constant and order the same, so enter. So now I calculate the error, right, that is equal to the what do we say, the rate, actual rate, right, minus the model rate, and enter. And let us say now I need to just be able to drag drop this, right, and the square of the error is equal to bracket, I guess, okay, bracket close to the power of 2 and enter, right. And now I need to be able to calculate the sum of squared errors or sum of all these errors. So that is going to be equal to sum of this and enter, right. So now I have sum of squared errors calculated for a trial value of the two variables that I am trying to find. The two variables are k and n. So I started out with the trial value of 0.5 and 2, right, and then I calculated the sum of squared errors, right. Error, how did we calculate that? Just between the actual rate, the error or the difference between the actual rate that we measured, let us say, right, and the model rate based on the relevant constants that you chose as a trial, right. So here I guess we are going to look at data analysis, right, data, and then go to solver, right. So Excel has this particular add-in, let us say, right, if you do not have this particular add-in, you can just go to options in Excel and then add-in and add this solver and data analysis tool pack, right, if you do not already have that installed, I guess, right. And how does this help us now, right. So here I have sum of square, a value for sum of squared error for a particular value of these two variables, which are rate constant and the order, right. So solver, let us say, will help me in, let us say, changing in or going by trial and error, I guess, change the values of k and n such that the sum of squared error is going to be minimum, right. So let us look at that, I guess. So the target cell, I guess, is going to have to be G11, so that is set, and I want to have a minimum, let us say, right. The value needs to be the minimum it can be by changing which cells now, by changing k and n cells, right. So let us say solve, okay, and I guess it solved for it, and I came up with some particular solution here, but because let us say my initial values were way too off, I guess, right. Looks like I have a relevant what do we say erroneous values. So I will try it out with what is a new set of values, I guess, right, because I know the k can't be negative, right. So there are many aspects, so let us go with k to be 0.5, okay, and let us say n to be around, let us say 1, right. And now let us run solver again, so that I am just starting with the trial value now, right. Earlier I guess solver had issues converging on solution, but you do know that the rate constant cannot be negative, right. So here again I am trying to assist the solver in arriving at the solution, right, or get converging at the solution. So I am choosing values, let us say, which now let us say have a smaller sum of squared errors, right. So the closer you start to the true value, the easier it is for solver to be able to solve this. So I am going to repeat that, right, and I guess everything else is going to be said the same, right, okay, and I am going to say solve, and I guess now I have the relevant values. So now you see that the sum of squared errors is the minimum it can be 120.8, I guess, and for which values is it minimum? Looks like for values of k to be 0.28 or 229 and n value of 0.91, right. So I guess here we are done with the first part of our question. So let us go back to the question again, right. So what does it ask us to calculate? Calculate the fractional order of the reaction using R equal to Kc to the power of n. So how did we go about that? We had time and concentration, we calculated what do we say dc by or minus dc by dt, right, which is the rate, and then we calculated rate modeled, right. And how did we do that? By assuming some value of rate constant and fractional order, let us say, or order of the reaction. We calculated that, we calculated the error square, and then calculated the sum of these squared errors, right, and then we asked Excel to change the values of k and n to be able to minimize this value of sum of squared errors, right. So from that, what values have we arrived at? So k we arrived at to be 0.29, k we have 0.29 and n to be 0.91, I guess, right. So in general, I guess this is the experimentally observed fractional order, but you know that theoretical values usually they are integers, let us say, right. So obviously I need to round that off, right. So the theoretical value should be 1, I guess, right. So let us look at the second aspect now and look at how to go about that, right. And the second aspect, I guess, obviously says, obviously we need to round the fractional order to the nearest integer, right, and that is what we did here. Now the n or order is equal to 1, right. So now what is the rate equation? R equal to Kc, right. So this is what we have now, right, to the nearest integer, and calculate the rate coefficient. So now that I change the value of n, I mean we have, I guess, k value we got to be 0.29 and n to be around 0.9, right, but now I am changing the value to what would be a reasonable value, right. N I know should be 1, right, if it is near about 0.9, and now what is now the value of k, right, that will again be or or lead to the best fit model again, right. So that is something that I need to do now, right, but the question, I guess, what does it ask us to do? It again asks us to calculate the rate coefficient or the rate constant k using a concentration based approach though, not R versus C, but C versus let us say time though. And also I guess we have two aspects to look at, linearized and non-linear regression, I guess, right. So let us look at what it is that we need to consider, I guess, right. So before we go further, I guess we need to understand that the form of this equation is dc by dt equal to minus rate of loss, right. So to be able to look at the concentration based approach, obviously I need to modify my particular equation here. So dc by dt equal to minus rate of loss, but from my particular calculations, so now I know it is equal to Kc, right. So that is equal to minus Kc, right. And for this, I guess we know that I solve for this from 0 to t, it is going to be equal to Ct is equal to C naught into e power minus Kt, right. And why is that? Again, this is a batch reactor, and from my calculations that I know that the rate of loss is equal to Kc and first order. So for that first order I plugged in the relevant case and saw that Ct, not saw that, I guess, you know, we did look at this particular case earlier too, and it's straightforward too. The solution would be after integration Ct equals C naught into e power minus Kt. So here now we have two approaches to consider, right. So one is asking for the linearized approach, right, and the other for the non-linearized, right. So linearized as in now I have Ct equal to C naught into e power minus Kt. This is the form of my particular equation. So I guess regression there are different ways, right. You can transform this equation to make it linear. So how can I do that? Let us say I know Ct by C naught equal to e power minus Kt, right. So natural logarithm of Ct by C naught is equal to minus Kt. So now it's linearized and I can conduct the regression on these aspects, I guess, right. So what would I conduct the regression on? I would conduct the regression on, let us say, Ct by C naught in one particular set of data and time in one particular set of data, right, and I am going to repeat the same approach, right, calculating the error and so on and so forth, and then I guess I will calculate the, what do you say, Ct by C naught modeled, right, for which how would I do that? I need to assume some value of k, right, it is going to be equal to minus Kt, right, and I have time here, so I can calculate the modeled value of Ct by C naught, right. I need to obviously for that assume a value of k. So I am going to go ahead with that. So once I have the true Ct by C naught and what we see modeled value of Ct by C naught, I can then calculate the error or the difference between them, right, and then the square of the error, right, and then I will calculate again the sum of squared errors, right, the sum of all these squares, and then again what am I going to do? I am going to ask solver, right, to let us say minimize this particular sum of squared errors, right, this particular cell by changing this cell of k, right. So again let us go ahead with that approach here, and let us say I have set it up in 2 here, right. So let us say this is equal to ln. So I am taking the natural logarithm of what we say here. I am going to assume C naught is going to be a constant. So right, its Ct is first this case this divided by 195 and bracket close and enter. So what am I doing here? I am just calculating natural logarithm of C by C naught, right. So same case here, I just use the same, what do we say, equation here for all the cells here. So now obviously I need to be able to calculate the modeled, what do we say, natural logarithm of C by C naught. For that obviously I need to choose some value of k. So I will start with, let us say, the value that we had earlier, that is equal to 0.29, I guess, right, or 28, anyway that is fine. So let us go with equal to minus k times t, and where is t? Into time here, right, and obviously I need to keep the cell constant with respect to the k, and so I have to say control Z, dollar symbol. So I guess this helps me in keeping the cell constant, again dollar symbol, right. So enter, okay, and I am going to use the same formula here. So now I have that here, right, and again why did we have enter please, okay, and why are we looking at minus Kt? As we looked at it here, right, we know that what is it now, natural logarithm of Ct by C naught equal to minus Kt, right. To be able to calculate the model value of natural logarithm of Ct by C naught, I am assuming some value of k and then calculating this model value of Ct by C naught, right. So that is the approach, and that is what I have here, and the I have a trial and error, or what do we say, trial value of k here, and so the error obviously is equal to the difference between these two values minus enter. So I am going to use the same here, and then is equal to this cell to the power of 2, right, and now let us say this is equal to the sum of all these, yes, enter, and this is the sum of squared errors. So again now I am trying to calculate the rate constant that would give the least sum of squared errors, right? What would that mean? That would mean that the k value would be closer to the true value, right? So let's try to approximate that. Again, go back to solver, right? And then the target cell is obviously this error, right? And it has to be the minimum, and by changing which cell, I guess, right? It has to be K2, okay, it seems like it's set at K2, right? Okay, and I'm going to ask it to solve it, right? F11 and K2, okay, solve, and looks like I end up with a value of 0.21, and now you see that the error has decreased, I guess, right? And so now you see that we started out with, what do we say, a value of k to be around 0.29, but looks like the model or the value that would best fit the given data would be your value of 0.21, I guess, right? So let's just write that down here before we move on, right? So from linearized, we have a value of k to be 0.21, right? So now for non-linear approach, I guess, non-linear approach as in I am going to, what we say, not transform this equation any further. So I have Ct equal to C naught into e power minus Kt, right? And let us say I am going to look at this particular case, right? And then what do we say, without transformation, just look at the relevant value of k, come up with Ct modeled, right? And how do I calculate Ct modeled here? If I take some trial value of k, I know C naught, or I am taking C naught in this case to be a constant, which is a good enough what do we say, assumption. Or if you want to, you can also assume that C naught is also a variable, let us say, but in general the first value that you have, let us say, is something something, let us say, in which you have greater confidence, let us say, right. So if you want to, you can also have C naught as a variable, or let us say in this case we are going to have C naught as a constant. So from that, let us say I am plugging in some trial value of k, and I know different values of t, right. I can calculate my Ct modeled, right, and I already have Ct, the concentration experimental values already given. Again I will calculate the error square, and so on and so forth. So let us move on. So here I guess I set it up, right. So that is equal to C naught is 195 into capital EXP, so exponential of minus, and I need to take some trial value of k, so I guess I will refer to this cell, and I am going to change the letter into, and time here bracket close, and also we need to edit it such that I am going to keep this cell constant, dollar symbol here, and again dollar symbol, enter, and k value, let us say again I am going to start with my trial to be around 0.29, right, okay, and then I am going to just copy this here. So here we have the modeled values for this based on, let us say, what do we say, this particular trial value of k, right, and then error is nothing but the difference of these two cells, right, equal to minus this, and enter, and error is equal to this to the power of 2, and now sum of squared errors equal to sum of all these cells, right, enter. So again what do I need to do again? I need to change the value of k so that I will get the minimum value of this sum of squared error, right. So again I need to go back to solver, right, and then let us say I am going to look at this particular cell, okay, I need to change E11, the minimum value, I am looking for the minimum. How do I get that? By changing I3, I guess, right, okay, looks like it's set, and I am going to solve for it. Okay, keep solver solution, and now looks like I have an error of, for an error of 152, let us say the k value is around 0.19, I guess, right. Okay. So now for this particular non-linearized what do we say, regression, I have value of 0. I believe 19, right, okay, 19, 0.19, I guess, right. So I guess depending on the approach, you do have, what do we say, minor variations in the model value, right. But if you want to compare two models, how would you do that, I guess, right. You are going to look at the sum of squared errors, right, and choose that particular model which would give you the least sum of squared errors. For example, here we have two rate constants, right, 0.21 and 0.19, and which one would you choose now? For that, obviously you are going to look at, let us say, the model or that model which will give you the least sum of squared errors. So let us look at the sum of squared errors for this. I believe sheet 3 corresponds to the non-linearized model, I guess, right. So here k was 0.194 and sum of squared errors was 152. Let us look at the other case. So, here I guess k was 0.21 for the linearized model anyway, and for the sum of squared errors is 0.43, but we can't compare that like for like, because here the error corresponds to natural logarithm of c by c naught. So, let us just calculate the c mod for this particular k value. C t equal to c naught is in this case 195, right, into exponential of minus k times, right, and k, this cell is a constant, so I will have to set it accordingly, right, into t, right, and t is here. So, I am going to say that is the case and enter and copy that here, right. And now I need to calculate the error for this particular case. So, again, why am I calculating the error? Because I want to have a like for like comparison of the sum of squared errors. So, in this non-linearized model we had the case for CT and calculate the error accordingly. So, here too I am calculating CT or the C model I guess, right. So, the error square I am going to calculate the error square directly, let us say here, right, is equal to C model 1 minus the actual, right, to the power of 2, right, and then if I drag drop that, and here is going to be the sum of squared errors, right, sum of squared errors, yes. And so, here as you see the error sum of squared errors with this linearized model, this is for the linearized model, right, is 404 for a value of rate constant of 0.21 I guess. But as you see here for a value of a rate constant of 0.19, looks like the sum of squared errors is lower, which is 152 in this case, and thus I guess the non-linearized regression actually gives us a better or the best fit model I guess, right. So, here I guess I have a few graphs that I would like to look at. So, let us go back to sheet 1, right. So, this is a particular case, right. Let us try to understand what we have been up to. So, here I guess the blue, what do we say, data sets correspond to the experimental values or the measured values, right. These two what do we say, data sets, and the rate or the red dot, let us say, or the rate model correspond to what we have, let us say, based on the values of k and n being what do we say 0.29 and n being 0.9, right. So, again you can look at that, right, rate model I guess, right. So, again as you see now, right, what is it that solver helped us do? It helped us what do we say come up with a set of what do we say constants that would best approximate the experimental data, which is the blue data point. For example, let us say if I change the value of k, let us see how this data changes. Let us go with 0.35. Okay, and now you see that the model values, let us say, are what do we say further away from what do we say the experimental values. Let us increase k further to 0.5, let us say. So, 0.5 again you see now further I guess there is what we say deviation from the experimental value, which is the blue data, and the red data set, which is the model data set. And again at the same time you see that the error has kept on increasing I guess, right. So, let us go back to I think what was our value 0.28 I guess, right, 0.28. Okay. So, now you see I guess the error is minimum, right, and also even graphically now or visually you can see that the model data set and the experimental data set are what do we say in consonance with each other. Again to illustrate this, let's say change n to let us say 2, and now you see that that makes no sense because the order I guess is now 2 rather than 1. So, let us go with 1, right. So, if we chose just n equal to 1 and k to be the same value of 0.29, you still see that there is considerable error, right, but you know that the order of the reaction, at least the theoretical value, needs to be what do we say an integer. So, thus we rounded off n to 1 instead of choosing 0.9, and then we calculated the k value, which would again see to it that this data set would what do we say or k value which would be the best fit, and I think we did that in sheet 2. So, here I have the data set, right, and let us say I am going to drop this here. So, here we have let us say natural logarithm of Ct by C naught versus time, right, that is what I have here. Blue data set is the true data or the experimental data, and red data I guess is the model data, right, and so that is what you see here. right. Even here let us say let us change different values of k and see how it changes. Let us go with 0.29, right, and you see that there is deviation from the data. Let us go with 0.1, right, and again you see deviation from the experimental values, which is the blue value, right. So the true value of k, right, would give you a data set or a model data which would see to it that the error or the difference between or the sum of squared errors when you look at it with respect to the model data and the experimental data is going to be minimum, right. So let us go back to, I think, what was our value, 0.21, okay. So now you see that this is minimum, I guess, right. So at the same time I also calculate CT, and this is the graph, right. So now let us go back to non-linearized what do we say, regression, right, and same case here. So here instead of natural logarithm of CT by C naught, we looked at C versus time. So again we end up with a value of 0.195, I guess, right, and for that again the graph, we have a graph here between the model value and the true value, right. Again visually too you can say judge that, let us say it is a pretty good fit, but how can you quantify that? You can quantify that by saying that the sum of squared errors is less or the minimum. So let us just try two trials here, 0.29, let us say, let us try 0.29, and you see that the model value now does not approximate the true values well. Let us go for a lesser value of 0.1, right, and now again you see the further shift to the other side of this set of data, right, and here I have the relevant aspects, I guess, right. Can I go back to the true value? Okay, so this is the true value, and you would have observed that the true or the best fit value, I guess, the sum of squared errors would be minimum, right. So if I also want to look at what do we say, different aspect, let us say what do we say, Excel has a few built-in options, let us say, with respect to trend line. So if you can go to that, let us say you can choose either between a linear or exponential model, but obviously it has a limited set of models, and then it can calculate, let us say, what do we say, based on again the same approach of regression, the value of the relevant variables, right. But obviously again that is going to be slightly different from what would be the true value, but this is the approach for regression that any model or built-in model would use, right. Again another approach would also go to say data analysis, and let us say this will not work for non-linear. So let me look at linear approach and demonstrate some other aspect. So I am going to go to data and data analysis, and let us say I will need to go to regression, okay, and regression. So input y range, I think here we were trying to look at what is it now, natural logarithm of CT by C naught, and what is it now, the time, I guess, right. And here again I can input the relevant values let us say, and then calculate again based on regression the relevant aspects here again, right. So let us try to get that done, I guess, right. So input y will be, I guess, CT by C naught, right. So y range, I guess, was the concentration. So I am going to say y data set, right, and okay, it should have been natural logarithm of C by C naught, delete please. So we are looking at the linearized version here, right, and so obviously I need to give the linear data or linearized data natural logarithm of C by C naught, and x range was, I guess, what was the x range, it should have been minus k times t. So I need to calculate that before I go further, right, or I can give t though, that should also work, right. And okay, so output range I am going to ask the data to be given somewhere here, okay, and I also want to have, let us say, residuals, I guess, right, and residual line plots, that is fine. And so here again there is a built-in tool, but usually works only what do we say, for linearized forms. So for that I am going to look at demonstrating how to get that done. So here I guess I have the output, right, and let us look at the values here, right. So intercept, I guess, came out to be, what is it now, 0.11, and x variable, which is your, what do we say, rate constant, is around your 0.22, right. So here again you see that this rate constant, right, again approaches the value that we calculated here, which was around 0.214, right, and that is what you see here, right. So again in the form of y equal to mx plus c, right, we see that the m is the slope here, and if you look at that natural logarithm of CT by C naught equal to minus kt, right, and in that case I guess k is nothing but your slope here, and that is the slope which is the x variable, which is minus 0.22, but you know it's minus KT model, so it's the K is 0.22, right. But here the model considered an intercept, that is why our x variable was different from what we calculated by our, what do we say, fundamental approach. So in your particular data analysis or regression, when you went there or when we went through that, if I set the intercept to be 0, I would have gotten the true value to be closer to the value of 0.21, I guess. So different approaches, but this approach that we have looked at is the fundamental value, I guess, right. So I guess with that we are done with the aspects related to kinetics, right. And now I guess from the next session we are going to move on to acids and bases, right. Again, kinetics give us an idea about how fast, let us say, a system or a process, what we say, goes through, I guess, right. And in that context today, what did we look at, let us say, in the second part of the session, let us say, we looked at, let us say, how to fit a particular data, let us say, pardon me, not a data, a model to a particular set of data and get the relevant constants so that they approach the true values. And for that, what approach have we looked at? We looked at regression, I guess, right. So I have a set of data, I want to calculate the relevant variables for the best fit. How do I do that? By minimizing the sum of squared errors, I guess, right. So I guess with that I will be done for today, and thank you.